Cool. Thank you for being patient with us. We were basically troubleshooting everything. But welcome to the very first Machine Learning at Berkeley workshop for this spring 2018 semester. We're going to be presenting on deep learning itself and try to give you a good intro to deep learning that maybe you can go and take the other workshops that we have offered. First things first, please make sure you have Jupyter NumPy and Keras installed. I'm sure most of you have done this already. Also remember to sign in at tinyurl.com/mlabintrodl. We just like to take attendance just to kind of see the range of people who come, see if people come a lot, and so on. And also, please remember to clone the repo. It's just at github.com/mlberkeley introdl workshop. It's up here. I'll leave it up here on the board so you can see it. That again. So, a little intro about us. My name's Philip Kuznetsov. I am the president of MLab this semester, and I am a junior in EECS.
Hi, my name is Pravin Ravishankar. I'm a machine learning at Berkeley education officer, and I'm a freshman in EECS.
And our emails are here if you have any questions. Just as a note, we'll be posting all of our slides online so you can check them out afterwards.
Cool. So, there's a lot of hype about deep learning nowadays, and we've experienced it all the media outlets talking about how AlphaGo defeated the world's best player in Go, and that really caught my imagination, and I was really excited when I heard about that. So what can deep learning do? So one important area where deep learning is making a really big impact is in computer vision. So here, researchers are trying to use deep networks in order to have artificially generated videos of President Obama saying various things, given various audio clips. So let's see what their work.
Than the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
Especially our friends who are lesbian, gay, bisexual, or transgender. I visited with the families of many of the victims on Thursday, and one thing I told them is that they're not alone.
To demonstrate the power of the method, we apply the same input speech mapped to 4 different target videos. Note that all 4 are synthetic and have different lighting conditions.
The auto industry. To help families refinance their homes. To invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs. Not to mention the job training that helps folks.
Because our...
So here, researchers are utilizing convolutional neural networks in order to colorize a black and white film. By the way, we're going to talk about convolutional neural networks today. They're used heavily in computer vision. Now, here is research that came out of Stanford's Artificial Intelligence Laboratory. So here, Fei-Fei Li and Andrei Karpathy, the director of the AI lab at Tesla, used deep learning in order to classify various elements in pictures, as well as to do object detection. So given an image of an elephant, they're able to identify that there was a red shirt on a man, that the elephant was standing on the ground, even shadows created by the elephant. Now, we can even see that one can train convolutional neural networks in order to recognize the 3D poses and the skeletal structure of various people dancing. Oh, maybe we should play this on full blast. That's enough. Right, that's enough. Oh, whoops. Huh? Oh, yeah. Okay. So another area where deep learning has a really cool application is in style transfer. So we can see the original image is in A, and we can apply different styles to that particular image to generate all these funny looking and somewhat interesting pieces of artwork. Okay, so now we talked about computer vision and image processing. So a second area where deep learning is making a huge impact is in reinforcement learning and control. So how do we train AI agents to do various tasks, such as playing various games? And that's where reinforcement learning comes in. So here we see research from Google DeepMind and how they used deep reinforcement learning in order to make sure that a game of Atari in order to have a computer play Atari Breakout at a superhuman level. So initially, as you saw earlier, the computer was really bad in terms of moving the ball with the paddle. But as the computer trains, and as the neural network becomes better and better, we see that it becomes better and better in terms of breaking out of that maze and escaping. Self-driving cars, enough said. Well, here they use a lot of convolutional neural networks as well as control theory in order to control self-driving cars. So here's an example of Tesla's autopilot technology. Now, we talked about computer vision. We talked about how deep learning can be used to control autonomous agents. Now we're going to talk about a third area where deep learning is making a huge impact these days, and that is specifically in terms of modeling relationships between input sequences and output sequences. So what do I mean by sequences? So, like any language is a sequence of words. Likewise, music is a sequence of sounds. And deep learning, with specifically a type of neural network called a recurrent neural network, one can model these relationships between input sequences and output sequences. So let's see how these researchers are using recurrent neural networks, or RNNs, to generate music that mimics the style of Chopin. This is all computer generated. All right. So here, this is a video from MIT's Computer Science and Artificial Intelligence Laboratory. So given a video of somebody hitting any random object with a stick, the researchers are trying to train a neural network that's able to predict the sound that's associated with that particular hitting action, as you can see in the video.
We conducted a human study where we asked people to distinguish real impact sounds from sounds that were synthesized by our models. We found that our sound predictions fooled participants more often than those of baseline methods, including simple image matching models.
It's kind of
All right. So now let's talk about why neural networks are so powerful. So as you can see here, and as many of you have probably seen already, this is how the basic structure of a neural network looks like. Now, neural networks are, in that essence, really powerful function approximators. That means that they're able to approximate really well a functional mapping from a set of input data to a set of output data, and that's what ML is all about, right? So neural networks specifically are very powerful because they can build complex and more and more complex hierarchical interpretations of our input data. So what do I mean by that? So let's say you have an image of a dog, and this image is a bunch of pixels. And those particular pixel intensity values are the inputs to our neural network. Now, in the first layer of our neural network, we might ask really basic questions, like, are there patches of lines? Are there ovals? Are there triangles? And in the next layer, called the second hidden layer, we might ask even more complex questions, like, is there fur? Are there two eyes? Are there two ears? Is there a nose? Finally, with all the information from all these questions and with all of the activations, that's the terminology that we use, that come from all of these neurons, we're able to ask ourselves the final question: is it a dog? And we're able to tell our final classification, yes or no. So the reason why deep neural networks are more powerful than maybe other types of machine learning is that they enable us to ask more and more complex questions, and they enable us to build more and more complex representations of our input data. And other machine learning methods are not so good, or may not even do this. So here, we go to the example of computer vision. And so in computer vision, as we mentioned earlier, we use a lot of convolutional neural networks. So as you can see over here, in a neural network for image recognition, the early layers will learn more fundamental features of the image. So in the top one half of the image, you notice a lot of black and white edges that seem to be oriented in various different directions. So what we notice here is that these particular neurons in the early layers are recognizing black and white edges that are a part of the image that are in various directions. And here we can see that these particular neurons are recognizing color gradients of different colors and of different intensities and in different directions. And so the early layers, nice visualization, learn rather simpler features. So now we're going to talk about AlexNet. So AlexNet is an example of a convolutional neural network. Philip will talk about it more later. But basically, as we can see here, earlier layers like layer 2 will recognize maybe the particular shapes of a dog's eye, for instance, while later layers might recognize the dog's entire face. So that's where we see the neural networks build more and more complex interpretations of our original data. So now let's talk about the basics of deep learning. So let's have a survey of the whole audience. So, okay, so raise your hand. I'm pretty sure you all know what a neural network is. Do you know what raise your hand if you know what the gradient of a function is? All right, most of you. Sorry. Raise your hand if you know how backpropagation works. All right, some of you. Okay, so let's talk about the most fundamental unit of neural networks, which is the neuron. So as we can see here, a particular neuron can be represented as a little tiny circle. And we have multiple inputs to the neuron. And each of these inputs are represented by each xi term. So imagine there are n inputs, then each input can be x1, x2, all the way to xn. In order to compute the output that is outputted by a particular neuron, what ends up happening is that we multiply each particular input by a corresponding weight. So as shown over here, then we sum this across all of the inputs. Then associated with every particular neuron is a term called the bias. So we add the bias for this particular neuron. And finally, this particular sum, this particular linear combination of the inputs added together with the bias is called the weighted input into the neuron. And we apply a particular function called an activation function. So here, in this particular slide, sigma represents the activation function. And once we feed this weighted input into the activation function, that becomes the neuron's output. So we can also vectorize the computation. Let's say W is a vector of weights for this particular neuron, and X is a vector of the inputs to that neuron. Then we just take the inner product of the weights and X, add the bias term, and apply the activation to compute the output. So having talked about the neuron, let's now talk about the layer, because that's the next level that we're going to talk about. So as you can see, a layer is, of course, a bunch of neurons that are stacked on top of each other. So we're going to take our vector of weights. So if W1 was the vector of weights for the first neuron on the top, if W2 was the vector of weights for the second neuron, and if W3 was the vector of weights for the third neuron, we're going to assume that each of these are row vectors. Then we can stack them row-wise to find a weight matrix big W for this entire layer. Now, what do I mean by the weight matrix? I mean that if you were given a bunch of inputs over here, and you multiplied these bunch of inputs by the weight matrix, you would get the weighted input to the neurons in this particular layer. We're going to talk about that more. So yeah, as you can see, what we can end up doing is, if x represents a vector of inputs to this layer, we multiply that by the weight matrix W. Then we add a vector b. Now this vector b is a column vector, where each particular element of the vector b represents the bias for the top neuron, the middle neuron, the bottom neuron. And then, so we get a vector consisting of all the weighted inputs to the three neurons. Then we can apply the activation function, which we'll talk about more, to every single element in this particular vector to get the outputs of all the neurons as a column vector. And we do this so that we don't need to do the computations for individual neurons, but rather we can think about the neural network as a bunch of layers and do the computations thinking about the layers. So let's talk about the structure of the basic feed-forward neural network. So as you can see, there's an input layer, a hidden layer, and an output layer. So usually when we're trying to discover the set of parameters and optimize this neural network such that it really works, there are no parameters associated with the input layer, because the input layer is just the inputs to our model. So as you can see, this is layer 0, layer 1, layer 2. So if x represents, if that neuron represented x1 and this represented x2, you get the idea. Then we can multiply the weight matrix for layer 1, which is this layer, by x, and add the bias vector for this hidden layer, layer 1. Then apply the sigma function, and this whole expression over here, that represents the output of this hidden layer. Then the output of this hidden layer is the input to this output layer. So all we need to do then is multiply this particular output by the weight matrix for the second layer, add the bias vector for the second layer, and finally put it through the activation function, sigma. Does anybody have any questions? No?
Actually, I have a question about the input layer. So like x1 and x2, can you give like a quick example of what those could be?
So we talked about the dog. So each pixel intensity in the image should be represented as an input. So imagine that you had a 10 by 10 pixel image, and obviously there are 100 pixels in that image. So imagine unrolling that into a 100 dimensional vector, just boom, putting it there.
Okay.
Well,
Yeah.
in the 2Ks, let's say we have a really simple data set, we still have dogs and cats, but the difference is is it furry or is it big or something like that, and that's our two inputs. So it's a one if it's furry, and another one for the other element for x2 we ask whether it's big, and so if it's big we put a 1 and so on. So it could be something simple like that. Yeah.
All right, so let's now talk about activation functions. So these are the functions that we mentioned earlier that generate the output from the weighted input to a particular neuron. So in the old days, when?
10 years ago?
10 years ago. They used the sigmoid activation function a lot. And the sigmoid function is denoted by 1 over 1 plus e to the power of negative x. So let x denote the weighted sum of inputs. Then take the weighted sum of inputs, put it through this function, and you get the output of your particular neuron. More preferable to the sigmoid is hyperbolic tangent, or tanh. And as you can see, while the sigmoid goes from 0 to 1, hyperbolic tangent goes from -1 to 1. So people would prefer the hyperbolic tangent over the sigmoid activation function just because it can output a bigger variety of numbers, like even negative numbers. But what we'll show you next is like the best, or not the best, like the most commonly used in practice. So this is called the ReLU, or the rectified linear unit. And I don't know why it works really well, but in practice it works really well. Imagine that the weighted input to your neuron is represented by Z. Then what the ReLU does is just it outputs the maps of 0 and Z. So essentially, if your weighted input is negative, the neuron will just output 0. If your weighted input is positive, it'll just output that. So that's why. So you might wonder why the ReLU is really preferable compared to these earlier activation functions. Let's say your weighted input to your neuron was in one of these regions where the slope was 0 or close to 0. Then what people have discovered is that learning like the neural network will learn rather slowly if many of the neurons and their weighted inputs are in this particular range. It has to do with the slope of the curve. But with the ReLU, those concerns are like mitigated, I guess. Now let's talk about why activation functions are needed in practice. So if you didn't have an activation function, then your output, the output of the neural network would just be a composition of multiple linear transformations or matrix multiplications. And as a result, you can only fit linear functions to your particular network. Your neural network can only fit linear functions. By using activation functions, you introduce a little bit of nonlinearity, and you allow the neural network to be a lot more expressive in terms of being able to, express, different functions, and that's what you want. So now let's talk about how deep networks are trained. So we're going to talk about partial derivatives, gradients, loss functions, gradient descent, and like backpropagation. All right. So yes. So like you guys all know partial derivatives and what they are, but we'll just go over them again. So the partial derivative of f with respect to x, we treat that if f is a multivariable function, we treat y as constant, and we change x and see how f changes. And here the partial derivative of f with respect to x of x squared y is 2xy. We take the partial derivative with respect to y 2 and get x squared. So let's talk about computing the gradient of the function. So let f be a function consisting of n variables. Then f of x, which is of course a multivariable function consisting of n variables, has a corresponding gradient where you can take the gradient with respect to x as the partial derivative of f of x with respect to x1, the partial derivative of f of x with respect to x2, the partial derivative of f of x with respect to xn. Really straightforward. Okay, so now let's talk about how neural networks learn. So we're usually given a data set, and that data set consists of n different images, as well as labels, or in case of when you're trying to predict a quantitative output, some type of number. And you usually choose a loss function for your particular machine learning task. And here in this toy example, our loss function will be equal. Our loss function for a particular training example x will be equal to 0 if our neural network represented by the function f correctly classifies that particular image or training example. So if f of x equals y, the loss is 0. Now the loss will equal 1 if the neural network does not correctly classify that particular training example. And our goal is to minimize the loss function. So that's basically our goal in terms of training this particular neural network. So let's talk about all the various loss functions that are commonly used in practice. So if you're doing categorical classification, you would want to use a loss function known as the cross entropy. It's really similar to the loss function that is used in, let's say, logistic regression, but generalizes to the case when you're trying to classify amongst n different classes, for instance. Here we are talking about the mean squared error, which is used if your neural network is trying to predict some type of numerical output. And you can click on that particular hyperlink to get a better explanation. Basically, loss functions must be easily differentiable if we're trying to minimize them. And our goal is to always minimize the loss function in order to find a set of parameters in our neural network that perform the best. Any questions so far? No? Okay, so now let's talk about gradient descent. So let our cost function be denoted by J of W, and that's the average of all the losses for every single training example. So note that the cost function, J of W, is a function of the weights of the network. So we can represent W as this really, really huge vector consisting of all the weights in our particular neural network. And so people use a technique known as gradient descent in order to find the minimum of our cost function. And so the way gradient descent works is that we update our vector of weights through several iterations. So here in this particular graph, we're kind of assuming that we only have one weight, but in neural networks you might have millions and billions of weights. So we'll just see how gradient descent works for the simple example. But as you can see, everybody knows that the gradient points in the direction of steepest ascent. And so if you want to try to minimize your cost function, you want to try to move your the ball, in this particular metaphor, down the bowl. And so what that means is that you'd want to update your set of weights so that it would move in the opposite, in the direction opposite of the gradient. So usually what that means is that we can update our set of weights via this simple update rule. The new set of weights equals the old set of weights minus a learning rate, denoted by n, times the partial derivative of the cost function with respect to that particular vector of weights. And we can tune this particular learning rate. So if your learning rate is really, really small, it might take a really, really long time to reach that minimum. However, if the learning rate is really large, you run the risk of going, let's say, all the way over there. And you would totally bypass or skip that minimum. Or there's a possibility that you could. So now let's talk about backpropagation. Now, backpropagation is not an easily explainable concept. We will try to explain the basics. We'll point you towards many resources. But our loss function essentially gives us an idea of how well our neural network is performing at any single moment. And we can use this particular loss function in order to update our weights and biases of our neural network repeatedly using the method that we talked about earlier, gradient descent. So backpropagation basically relies heavily on the idea of the chain rule from multivariable calculus. And in order to introduce backpropagation, let us introduce the concept of the so-called quote-unquote error of a particular neuron. So the error of a particular neuron refers to the partial derivative of the cost function with respect to the weighted input to that particular neuron. So let me give an example. So let's say we have a neuron like this, right? So we have our cost function for the whole network, and the weighted input for this particular neuron represents the set of weights, multiplied by the corresponding input values plus the bias. Now, the partial derivative of the cost function with respect to each particular, with the partial derivative of the cost function with respect to the weighted input for a particular neuron can be used as an indicator that shows the amount of error for that particular neuron. Now the way how backpropagation works is that we compute the errors for all the neurons in this final layer, then compute the errors for all the neurons in this layer, then compute the errors for all the neurons in this layer, and so on and so forth. So essentially we backpropagate our errors after seeing how well our neural network does on a test set, or I'm sorry, on the training set. And using these errors and all these partial derivatives, we can use a lot of multivariable calculus and a lot of chain rules to compute the partial derivatives of the cost function with respect to every single weight and bias, every single parameter in a neural network. So essentially, neural networks were mostly, while the idea of a neural network was there for a long time, when researchers in the 1980s, I believe, when researchers in the 1980s discovered the backpropagation algorithm, that was when neural networks became very, very practical. Because how on earth could you compute the partial derivative of the cost function with respect to every single parameter in your neural network with just two passes in this neural network? A forward pass to evaluate how well the neural network is doing in any particular instance, and a backward pass to examine the error for every single neuron. Using just two passes, we can compute all these partial derivatives, even if our neural network has millions and billions of parameters. And the reason why we need these partial derivatives of the cost function with respect to every single parameter was because we use these partial derivatives in gradient descent to update the weights and biases of our neural network to make sure our neural network is really good in doing whatever job it needs to do. So essentially, to repeat what I just said, the slope of this layer, partial derivatives, depends on that layer, which depends on this layer, and so on and so forth. So here are the actual equations of backpropagation. There's a really good online resource that we'll point out at the end, which you can show. It has a really nice proof of all these four equations. And essentially, well, we won't go over the details. The first equation tells you how to compute all the errors of all the neurons in the final layer. Let's note that as capital L. The next equation explains how to compute the errors of all the neurons in the layers before that. And based on all these errors, which we denote as delta, you can compute the partial derivative of the cost function with respect to every bias and the partial derivative of the cost function with respect to every single weight from these error terms. So these four equations are known as the four fundamental equations of backpropagation. And we won't see this video, but it's in the slides. It's a really good, basic understanding, explanation of backpropagation. So to recap, neural networks are composed of layers of matrix multiplications with an added nonlinearity at the end. We need lots of data, as well as a very good loss function to train a neural network. Neural networks learn by calculating the gradient of the loss function, and then they descend this particular gradient descent. Neural networks build abstractions on top of abstractions while learning to make complex decisions. Essentially, they have different layers that together do more and more complex tasks, similar to how we think the brain works. That's why they are far more powerful than most other machine learning algorithms. All right, does anybody have any questions? Yes?
You said something about you do first pass and then you do another pass backwards. Can you explain what the passes are?
Yeah. Going back to that particular image. So backpropagation actually has two passes through a neural network. There's a forward pass and a backward pass. So let me explain more in detail. So imagine that you have a set of weights and biases in your neural network to begin with. You want to know, based on your current set of parameters, how well the neural network is doing in terms of on your training set. So you use your current set of weights and biases to take your particular input, which could be like the pixels in your image, and you forward propagate, or you walk yourself through the network. Remember, we showed doing the matrix multiplications as the biases, apply the activations for every single layer, and then we get the output, and then based on the output of the neural network, we can compare that particular output versus the actual label or actual output in your training data. So that was the forward pass. Now, then intuitively, based on how off your prediction was compared to whatever your actual data's label was, you can compute the errors for neurons in this layer, then backpropagate using the chain rule, the errors in this particular layer, the errors in this particular layer, and the errors in this particular layer, and then use the errors for all the layers in order to compute the partial derivative of the cost function with respect to every parameter, which essentially allows us to then update all of our parameters at the same time using gradient descent. So that's how one iteration of like an update would look like, and that's why you need two passes, a forward pass and a backward pass. Any other questions? No? Okay. All right. So, should we take a break? No. Okay. So now we're going to talk about deep learning for MNIST digit classification. So MNIST is like a huge data set of digits collected by the United States Census Bureau, and they had employees of the Bureau and high school students write down all of these digits from 0 to 9 and have the computer distinguish between these 10 possible values. And we will see that we can train a neural network. We're going to do a demo right now that can accurately classify all these images with a 95% probability, accuracy. Yeah. Of course, like our neural network isn't really optimized. It's just a demo, and this is a regular neural network. Nothing special. Like Phil will later talk about convolutional neural networks. That's way better for this particular task. So let's talk about coding up the MNIST demo. So you need Jupyter and NumPy for this task. So we won't be using any deep learning libraries. This will all be from scratch Python code.
Also, all of this is in our intro DL workshop. So if you come in late, please git clone this, and you'll be good to go. I think you're good to go.
All right.
Yeah, I got you. Cool. Can everybody see everything on there? Raise your hand if you're having a hard time and we can zoom in a little more. Oh, let's zoom in a little more.
Let's wait for everybody to get this stuff open. So
We'll wait like another minute.
Yeah.
For anybody who's still setting up. Actually, raise your hand if you're still setting this up, and we'll wait for you. Okay, cool.
There seems to be an issue with Calvisi. I cannot access Github.
You cannot access GitHub.
Oh man.
Restart your turn on and turn on your Wi-Fi. There's an issue with the system Wi-Fi right now, so it's pretty annoying.
So github.com, ML Berkeley Intro DL Workshop.
Did it end up working? Still not working.
Is there a way to put it on like Bitbucket or something? Does that work?
Wait, GitHub doesn't work on Calvisi, but Bitbucket works.
Yeah.
We probably can't do it right now, but maybe you can access it later then. We try to write up the instructions, and you can try to follow along now. If you have Jupyter installed, you can try to like type up some pieces that we're writing here. But at the end of this, we'll actually upload all of the solutions, all the stuff that we have written for this.
Wait, who do you want to ask who here? Like, has it open or something?
Did anybody successfully open it? Raise your hand if you successfully opened it. So maybe you can peek off of some of their screens, if that's cool with everybody. Or you can peek off us. We'll walk through every step, so it should be pretty clear.
So let's go. So we need to import random. We need to import numpy.
Yeah, it's just
we need to import. Make sure you fetch all the files. So MNIST loader is a module, so it's another file that we used for reading data from like a serialized version of all the images that we use in order to classify for MNIST.
you run it.
Huh?
You should run it.
Run what?
The first cell.
Yeah. Sorry. Okay, wait.
Yeah.
Okay.
It's all good.
It's kind of zoomed in too much, but so essentially what we now do in this particular line is we just load our data, our training data, our validation data, and our test data from a version serialized on our disk. Everything's in the GitHub, all the data.
I don't think you ran that.
Wait, right?
I didn't. No. I think you let go too early. Just do it.
Okay, shift enter. Okay, so now let's talk about the deep feed-forward network class. So essentially this class represents a deep feed-forward network. We essentially talked about feed-forward networks, regular neural networks. And so now I'm going to walk you through the constructor for this particular class. So this constructor will initialize our deep neural network. So it takes in a parameter called sizes. So a possible input to the constructor for this neural network could be, let's say, 3, 6, 8. What this particular parameter value for sizes would indicate that there would be three neurons in your first layer, six neurons in your second layer, and 8 neurons in your final layer. All right. So I'm gonna write some code. Number layers equals the line of sizes. So the length of the list, of course, represents the number of layers. Self.sizes equals sizes. We also have, oh, whoops.
Yeah, I've inverted the mouse.
Oh, that's kind of hard. I'm going to write some code, but I promise I will explain it. And a little bit too much for this screen. Okay. So let me now talk about what this does, basically. So most of you are probably familiar with Python indexing, but sizes 1 to the end will basically, in our list, if we try to splice that list, we'll just get 6, 8, and we'll drop the 3 since we start from the first element. And what this will do is, it's a list comprehension in Python. So what it will do is it will create a list consisting of a bunch of bias vectors for every single layer. So what do I mean by that? What I mean by that is that this is a list consisting of 2 elements in that particular example. The first element is a vector of 6 elements representing the randomly initialized biases for the middle layer. And the second element of this particular list is a vector of randomly initialized biases for the final layer. And of course, we do not include biases for the first layer because the first layer is just a set of inputs to our model and there are no parameters there to adjust. So now we're going to talk about self.weights, which is constructed in a similar fashion. And so essentially what we do here is we take sizes -1, which we take sizes -1, which is basically the entirety of the list except the 8 in the end, so just 3 and 6, and we zip that together with sizes of 1 to the end, and that is
6 and 8.
yeah, 6, 8. And we zip that together, and essentially what ends up happening in our particular example is that self.weights is now initialized to be a list where each particular element in that list is a weight matrix for a particular layer. And each of the elements in the weight matrix are randomly initialized. And this code basically fixes the dimensions of the weight matrices for all the layers correctly. Anybody have any questions? Sorry, we're going off to a slow start, but all right, moving on. Okay.
Other direction.
Oh, okay, sorry. So now we're gonna define feed forward as self comma a. So what does this method do? Let a represent the set of inputs to your model. How do you compute a vector of outputs given a vector of inputs to your neural network? Well, basically the whole idea is to repeatedly multiply that particular input A by the weights, add the biases, apply the activation functions, and then do this repeatedly over and over and over again for every single layer. So essentially what we're going to do is we're going to step through self.biases and self.weights for all the layers in order to do this like iterative computation and feed forward our input data to get our output data. All right, so let's now code this up. So So the reason why this piece of code works is because what this does is for each iteration of the for loop, B and W are assigned to be the bias vector and the weight matrix for a particular layer. And we take the matrix product or the matrix vector product of our weight matrix with respect to A, and we add the bias vector for that particular layer and apply the activation function, which in our case we'll just use a sigmoid function, and that will be the value of A. And we repeatedly change A until we get our final outputs. Does anybody have any questions about this? Yeah.
Oh no, do you mind scrolling to the end of self-weights?
Oh. Okay.
Okay, thank you.
Any other questions? Yeah.
Yeah. So the weights it's a matrix, right? What's the dimension of it?
Okay. Good question. Let's say that we are mapping from let's say we want to find the matrix of weights that go from the outputs of a layer with 3 neurons to a layer with 5 neurons. Then in that particular instance, we would have the dimension of the weights would be 5 by 3. So that's why you see that because it's flipped, we say for x comma y, but we're actually initializing a matrix with y rows and x columns. Any other questions?
So does that mean it's transposed?
It's not exactly a transpose. We merely write. It's a convention in deep learning that. Okay, this is something important, so I'm going to draw it out here.
Oh, use the other one.
What? Oh, sorry.
Oh.
Hopefully this gets in the webcast. But and we have a fully connected layer, remember? And so on and so forth. So this is a layer with 3 neurons. This is a layer with 4 neurons. Then matrix of weights for this particular layer will have 3 columns and 4 rows. Okay, that's where that comes from. That's why we flip y, x.
And you're right multiplying the input vector. That's why you may think it's like a transpose of it.
Yeah. So imagine taking your weight matrix, and if A represents, let's say, the outputs of layer 3, we just say W times A. Okay. So so now I use the function that we haven't defined, sigmoid. We're now going to do that. All right, so the sigmoid function. So when you're writing code for deep learning, you usually want to vectorize your code, which means that you want to be able to perform operations simultaneously at once on huge vectors and matrices. And this speeds up your code significantly. So what we're going to do here is we're going to define a function sigmoid, which takes in a vector of values z, and it applies the sigmoid function to every single element in this particular vector. So I'll do this rather quickly. We know, sorry, return 1.0. So yeah, our sigmoid is 1 over 1 plus e to the power of negative z, where z is the weighted input. And we can define sigmoid prime, or the derivative of the sigmoid function, which is really helpful when we're doing derivatives for backpropagation. And that's defined as, it's actually kind of interesting that you can define the derivative of the sigmoid as the sigmoid multiplied by 1 minus the sigmoid. So that was that. That gives you a little overview of how to forward propagate, or how to compute the output of a neural network given a set of weights and biases. We won't go over every single part of the training and backpropagation code, as it is a little bit hard to explain, and we'll direct you to other resources. But we just want to really quickly talk about this particular method called SGD. SGD stands for stochastic gradient descent. Now, we talked about gradient descent earlier, but the way SGD works is that instead of training your neural network on all of your data points in your training data, you basically pick a mini batch, which is the size of, let's say, m particular training examples. And you use that particular set of m training examples in order to update your neural network's weights and biases in one particular iteration. Then you do this with another mini batch, another randomly chosen set of m training examples, and you keep on doing this again and again until you have exhausted your training data. That's called one epoch of training. Here, when we call our neural network, or try to train our neural network using this particular class that we have defined, all that it will require is that we give the training data, which is like a tuple or a list of tuples of x and y data points, the number of epochs, or the number of times that we're using our training data in order to generate various mini batches, our mini batch size, which is the number of training examples in each particular mini batch, and ETA, which stands for the learning rate. Remember, in gradient descent, we had this coefficient that was in front of the partial derivative term, and the learning rate will control how fast we're going to make those updates to the weights and the biases. With that being said, let's try to run this neural network. Hopefully it works. Oh, we haven't coded up evaluate yet. So what evaluate does is that what it basically does is it just given a bunch of test data points, it just tries to evaluate the output of the neural network. What I mean is it will try, given test data, it will evaluate the accuracy of how well the neural network does in classifying that test data, new MNIST images. So test results equals np.argmax of self.feedforward. Remember, we defined feedforward as a method earlier that indicates what the output of our neural network is. I'll explain more of this code once I finish typing it, but oh, whoops. Be organized.
I think you made a space instead of an underscore.
Wait, do you want to correct it? I
Quickly
kind
fix it. No worries.
Yeah.
Yeah, it's right here.
Okay. Cool. Test results. So we can imagine that a neural network is going to output a vector of size 10, and that vector of size 10 represents how likely the prediction of the final model will correspond to the image having 0 or 1 or 2 or 9, and so forth. So basically what this first line of code does is it says for x comma y in this test data, feed forward that through the network to get the prediction of the neural network, and let's take np.argmax, which will basically say, hey, what number does the neural network think that this particular image corresponds to with the highest probability? We compare that against the particular, actual label in our test set, and then we compute the accuracy by finding the number of data points where they match, where the neural network is right. All right, hopefully this works. We're now going to train the neural network for the task of MNIST.
First.
So I'll just run all.
Run all.
Yeah. Hopefully it works.
I can help debug it.
I think there was an extra parenthesis or something.
Wait, where?
No, it would have thrown an error. We're good. It worked. It runs.
Hopefully.
Yeah, no, it's already running.
Oh yeah, it's running that.
Cool.
Yeah.
Oh wait, scroll down.
Yeah.
Keep it running. So.
Oh yeah. So I'll explain. So we're stepping through many epochs. You can see that initially our neural network gets it like 90% of the time, then 92%, 92.96%, so on and so forth.
And it'll basically just keep going and getting better.
Yeah. I mean, we could wait for it for like 30 epochs, but
Any questions?
yeah.
Just,
Oh, can you go back to the previous? It's kind of like scroll to the right.
which function?
Which function?
Evaluate.
Oh, okay. Whoops. Yeah.
Anything else?
What do you guys use to define your cost function?
Just mean squared error. Yeah, that's why we have this cost derivative function here. And remember how I mentioned how you first compute the errors in the final layer and backpropagate that. So we use the cost derivative function, which is like the derivative of the mean squared error, like loss, in order to compute the errors in the final layer. So that's what that function is used for.
We can see how far the accuracy's gone.
Oh wow, looks like it's not doing as well as it got, or it's doing pretty good.
94% is
Yeah.
pretty good.
Yeah, it'll eventually reach like 95, 96%. Yeah.
I guess
Keep training for a while.
we can take a 1 minute break. You can go to the bathroom, you can chill, but we'll come back at about 9. It's 9:16, 9:17 now. We'll come back at 9:18.
So basically, to preview the second half, we'll be going over convolutional neural networks, and we're going to use like a deep learning library in order to make this whole code like done in just like 10 or 20 lines.
Yeah. Yeah, we can come help you out with that. Do you have a question? Yeah, sure. So self-referential absolute bias, that means that your init is warming. And that's in,
This is as in like this was already provided.
let's see. Let's try
Yeah, that was right.
Maybe what happens is wait, hold on. But that's okay. Let's see. So there's actually not much. There's not much. Compare it to the actual answers.
So essentially, we end up with like 95% accuracy. If you use more sophisticated optimization methods, you can like boost that up to like 98, 99%. But here we're doing the most fundamental stuff.
Oh shit.
Oh, that is so weird. How about this? Restart. If not, I can just. Robin, you don't need these anymore, right? Here you go. You can try to find the difference. But the only remember the only things we did were so good luck. Oh, yeah, we'll also push it to GitHub. Okay. So it's been about 2 minutes, and as you can see, we finished training when we got about 95% accuracy. When we go back to the second demo, you'll see that we can get this accuracy pretty easily. The deep learning library we use is like very convenient for this kind of stuff, so it'll be very nice. Back to the slides. Okay, cool. So now I'm going to be talking about convolutional neural networks. Pravin touched a little bit on kind of like the concept behind them, but I think an important thing to realize is that the convolutional neural network is kind of the backbone for all of the deep learning hype you may have heard about in the past 5 years. The basic idea behind the convolutional neural network is that we introduce a new type of layer called the convolutional layer. This layer preserves a lot of spatial information. If you remember when we were talking about like setting or inputting a picture of a dog into a neural network, we talked about having to like unroll the image and then kind of like make this 2D image into a 1D large vector, 10,000 dimensions or 10,000 dimensional vector. So when you like perform that process, you lose a lot of the spatial information you would normally have with an image, where you basically know that like pixel A is next to pixel B and so on. Instead, you just kind of like throw random numbers into that neural network, and what can happen is you can just like permute those values and still get the same kind of accuracy because you now don't have this like natural relationship. The convolutional layer creates a structure that preserves this information. So this right here is an example of a 2x2 convolution, kind of frozen in time. And the key part of the convolutional filter, which is like related to the neural network structure, is this convolutional filter right here. So this weight filter is kind of like the analog to the weights in the fully connected network that Pravin was talking about. These weights are basically passed over an image one place at a time, and every place where it stops, we take the dot product of those weights and the values underneath them. So you can kind of see this exemplified here in this part of the image right here. So this yellow square represents the overlap of this filter on top of the original image. Here we basically multiply the weight filter by 1 here, 0 here, 1 here, 0, 1, 0, and so on. And then we get the output. Now after we do one step, we move to right one more step, and we do the same operation. The dot product of the image with the weight filter over that area of the image. And then here's a diagram. Here's a GIF of the entire process. Any questions on that? Cool. So here's another diagram. The input is the blue image at the very bottom. Is the blue, I guess, matrix at the very bottom. And then the output is the greenish cyan at the top. Yep.
Is the weight the same for all of the things you're doing?
Are the weights the same for each of those like places it lands? Yeah, the weights stay the same. It's just the image values change because you're looking at a different part of the image. Cool. So to kind of give you an intuition on how convolutions work, here are some examples of convolutions in image processing and computational photography. So this particular convolutional filter represents a blurring operations. It's known as the Gaussian filter. You may have heard about like a Gaussian blur. This is basically the operation. They take this filter and then they just pass it across the entire image, and it pools into this kind of like blurry looking image. Another type of convolution can be used for edge detection, or at least like highlighting the edges inside of an image. So this particular filter is pretty good at highlighting horizontal images, horizontal lines inside of an image. So you can see we take this picture of a bike rack, and then you can very clearly see the like horizontal edges inside of that resulting image. There's actually, if you turn this weight filter to the right, like 90 degrees, so that there's like a 0 in the center of this weight filter, you actually can get a vertical edge filter detector. Vertical edge detector. So in a convolutional layer, a single layer, we'll typically use many of these convolutional operations. And then each convolutional operation will produce a single 2D matrix slice of information. Then to kind of accumulate all of these together, we basically just stack these 2D slices, so then we get like a 3D volume of matrices. And this kind of gives rise to the notion of a tensor, which you may have heard used in contexts like TensorFlow and stuff like that. So a tensor is basically just like a generalization of a matrix in many dimensions. We typically just deal with it in like 3 dimensions when we're dealing with neural networks. And so you can just basically think that the input of a convolutional neural network is a 3D tensor, and of a layer is a 3D tensor, and the output of a convolutional layer is also a 3D tensor. Now, you may be a little bit confused because we were talking about images, and you're probably used to seeing images as 2D matrices, right? Basically just like 2D plane. There's no depth or anything like that. However, inside of our representation, and the representation typically used when you import an image into like NumPy or some other like matrix-based program, is they'll actually represent it as a 3D tensor itself, where the third dimension, the one that you weren't even thinking about, is actually represents the color channels inside of that image. So the red channel, the green channel, and the blue channel. And that's kind of demonstrated up here. So our imaginary image is split up into its 3 separate channels, red, green, blue, that produces the 3 different depth channels of our 3D tensor input tensor, and then we have the height and width of the image. We perform our convolution operation, which is now also generalized for this like 3D world. So this 2D tensor I was showing before, when we're actually applying it to images, it in fact is actually also a 3D tensor that we're dealing with. And so instead of being just 3 by 3 for the width and height, it actually will have a third dimension, which will match the depth of the input of that convolutional layer. So in this case, since we have 3 channels, the input will be, the convolutional filter will be 3 by 3 by 3. Does that make sense? Yeah, Charlie?
Would your input be like more than 3 if you did like several training examples at once?
So that's like a batch. That's when you start doing batch sizes stuff, and then you kind of layer it across a 4th dimension. That's where you start dealing with like 4D tensors instead. Now, I don't really want there is like an exception to that, and I can talk about that afterwards. But I don't want to like throw that into this presentation because that's more of like a nuanced situation. That we can talk about that after if you like. And so in successive layers, we now have like size, like depths of images, or I guess whatever the result will be after a convolutional layer, and we'll have those like data blocks that have f depth, I guess. Yes, F being the number of filters in the previous layer. So if we had another layer after this one, the convolutional operations will have a depth of F, corresponding to the number of filters here. Does that kind of make sense? Raise your hand if it doesn't really make sense, and I can try to explain it again. That's okay. So basically, because we want our convolutions to match the depth of the input volume so that they have the same depth, we make sure that, or we basically just literally assign them to have that same value, that same amount of depth. So let's say in this case, this blue is actually a color image, or maybe like this height by width by 7, whatever depth, maybe like a bunch of extra color channels for whatever reason. Our weight filter would not be just one of these like 2D matrices. It'd actually be 7 of them stacked on top of each other. That kind of makes sense. Okay. So convolutional layers have a few like parameters that are associated with them. There's the filter size. So in this case, in this case we just talked about 3x3 filters, but we can also vary that. Actually, that's something that's usually kept constant, but you can play around with that in reality. Strides represent the number of steps we make between each place that we look at inside of the image. So all the ones I've shown here have been a single stride, single step, but we can arbitrarily choose the number of steps we go through. And that, as a result, that'll change the size of the output volume. And then we can also do stuff with padding, which basically just adds zeros around the edges. And as you noticed here, we actually end up with a smaller image, but if we wanted to add padding around the edges, just zeros, then we could actually create exactly the same output image size by just ensuring that we have this padding on the side. And then dilation is a little confusing, but what I did provide is a link to a nice visualization of all of these different parameters. You can go check it out on your own, and it just gives you like nice diagrams on what the different parameters might look like. Any questions about that? Cool. So the convolutional layer is definitely the most important part of the CNN, the convolutional neural network. However, a key other piece of the convolutional neural network is the pooling layer. The basic idea of the pooling layer is that the purpose of the pooling layer is to downsample input in a clever way to kind of force the network to make decisions as it processes through them, or I guess like to force the network to come to a more specific decision, or at least that's what it's theorized to do. So in this particular case, we have an example of a max pool layer with a 2x2 filter and a stride of 2. What that means is it basically places a filter over one part, takes the max of that, and then outputs it into this part right here. So filter on this like red part, and that produces the maximum here. So the maximum's right here. And then it takes 2 steps over, so they're not overlapping at this point, and finds the max of this 2x2 square, which is this value here. Goes down 2 more steps because it's stride 2, so it steps down 2 in the vertical axis as well. Finds the max of this, and so on. So again, you actually have similar parameters. You have a filter size and you have a stride parameter, but additionally you have a type of pooling that you may want to perform. And the 2 common ones are averages. So basically, instead of taking the maximum, you just sum all these together and divide by 4. Or you could just do the max as I've demonstrated here. Any questions about that? Yeah.
So is that image right there? Is that like just one of those slices that you were talking about before, or?
Yeah, it would be one of those slices, and what you would typically do is I think you'd also have to define like the depth on how much you'd want to downsample within the depth itself. But I think mostly we actually ignore that. Sorry, you just ignore that and you just do it across each of the slices. So you accumulate the maximum across every single slice instead of through the depth. So you preserve the same depth output out of the max pool layer. Yeah. Cool. And this is a slide you've already seen. Pravin brought this up. So early convolutional layers end up learning edge detectors. It's just the way that backpropagation encourages what the backpropagation algorithm encourages the network to learn. And this just seems to be a good initial feature in the network. And then we can build up these edges to create more complicated, to understand more complicated structures like eyes, and then within a few more layers, we can use those complicated structures to then understand like dog faces. So typical layer order is a little confusing to explain, but it's basically just like we have a convolutional layer, we have a ReLU, and then we have a pool, and then we have some kind of variant. But we could also vary that. So after some layers of convolution ReLU, maybe conv ReLU, and then pool, conv ReLU pool, something like that, we then end up we then want to make a final classification, which will actually pass the final layer into a fully connected layer. And that fully connected layer will then pass into a ReLU, and then we may repeat that 1 or 2 times, and then we pass it to a final fully connected, which goes to our output classification. So I'll show a demo of this because this is kind of a lot to digest. Cool. So the first thing to know is you should have Keras installed. Should be pretty quick to install if you haven't yet. Just pip install Keras. And then I'm not going to go over these imports because it'll just take a long time, but we'll just let this run. And it seems like we're okay. So just so you know, Keras is a is a deep learning library that is built off of TensorFlow. It was originally an agnostic to like the backend deep learning library, but because the other option for Keras is backend, Theano, has stopped support, TensorFlow is the basic default. So the first thing I'm going to do in this demo is actually demonstrate how we can implement something like Provin's network in Keras. So first thing is just going to set the batch size to 128. The number of classes are equal to 10. It's the same problem. We're doing the MNIST problem. So there's 10 different digits. Oh, okay. Sorry about that. So yeah, we have 10 classes because we have 10 digits, and we're going to train for 5 epochs, basically just 5 passes through the dataset, the training dataset, and our learning rate will be equal to 0.01. So we're going to prepare the data, not going to go through this, but basically we reshape the data from a 2D image. By the way, the reason this is a 2D image and not a 3D representation is this data is black and white, so there's only one slice. There's no RGB channels, there's just literally like that one single channel. So there's not much nuance to that. Hopefully that's good. Okay. And now we can write the model. So the nice thing about Keras is they already implement a lot of the models for us. And so to make the model that that Provin made, we just need to write this. So we first define our model. This just defines that we're going to add models like one after another into making basically a list of layers. Our first layer will have 30 hidden units. So this is after the input. We'll just have like a hidden layer with 30 units. Let me see. Our activation function will be ReLU. And our input shape will be the shape of MNIST as a vector. So 784, because MNIST is a 28 by 28 image. The next layer will then just be our output. So dense defines a fully connected layer. I didn't mention that earlier. The number of units will be equal to the number of classes we have. And then our activation will be the softmax, because softmax is kind of like a nice way to get a probability distribution over all of the possible classes. So that's set. Oh, and I changed the learning rate. Sorry, I forgot that I left this. But the next thing, forgot a key thing. The cool thing about Keras is you can see like a summary of what your model looks like. So I put out model.summary. Then it'll show me the output shapes of each of my networks. It'll show me the number of parameters and just give me a total sum of all the parameters. Cool. So next thing I want to do is compile the model, basically prepare it for training. So I set the loss to categorical cross entropy. If you remember from the from the neural network loss function slide, this is one of the classic ones, and this one's used really for classification problems and cases where our classes are discrete. Our optimizer is going to be stochastic gradient descent, so that's just defined as SGD inside of the Keras library. I've already imported all of this stuff. And then our metrics, we can just set a metrics that will output while we're training, and we'll call that accuracy. I mean, it'll just be the accuracy. So now that that's done, all we need to do is run model. Oh, whoops. History. So we set history as the output, and I think this just gives us like the accuracies over time. And then we can just run model.fit. We pass in our training data, so that's xtrain and ytrain. X being the images, Y being the labels. We set our batch size to batch size. That was defined earlier. Our epochs, we'll just set our epochs to equal epochs, also defined earlier. It's equal to 5. Verbose just is like for extra printing. And then we can set validation data equal to our test data, just so you can see like our progress on a holdout set as we're training. So now, don't forget your commas. Okay, so now we'll run it, and you can see it trains pretty quickly. It looks really cool, and definitely looks really, really sleazy. I mean, really, really cool. So, and now we can see after about five epochs, it's trained to a validation accuracy of 95%. And this is the same value this is the same quantity that we got when we got the test accuracy from province code. Does anybody have any questions about that? Okay, cool. So I wanted to get a little bit fancier because Keras makes it really easy to write neural networks, and I wanted to add a few more layers. So what we're going to do is write a model that has these parameters here. So our input's going to be 784, and we'll just define that in the first layer. But first thing I want to do is just redo my model, add the first layer, which is going to have 512 units. That's this hidden 1 right here, with a ReLU activation. No, come on, there we go. Equals ReLU, and then we need to make sure we define our input shape is equal to that. Next thing we want to do is we want to add a dropout layer. So a dropout layer basically is a regularization layer. Other than like hand waving it, the best description I have is that it basically hides certain units with a certain probability from the training process, basically disables them from updating, and that way you are supposed to rely on only a few single neurons inside of that whatever layer is being like dropped out for the learning process. And this helps with generalizing, which means to like make it so you perform better on data that you didn't see during your training process. I have some good descriptions in the links in this like description here. So if you want to read more from people who can explain it better, please do. So I'll set that probability to 0.2. Then I will add, let me just make sure I'm doing this correctly. Oh no, it's not a big deal, don't worry about it. Add another layer that is also 512, set the right activation to ReLU. We don't need to do anything with input shape. Add another dropout layer, because why not? And then let's add a final layer, which has our num classes, and it sets our activation to softmax. Cool. So let's see what we get when we get our summary. Everything looks correct, and at least it compiled. So delete that. Sorry. Gonna compile the model now and evaluate it. Actually, I'll write it in the same thing. So compile. Actually, yeah, no, never mind. We'll set the loss equal to categorical cross entry again. Our optimizer will be equal to Atom. So Atom is another type of optimizer. I didn't make a link to it here, but it's just like a better version of SGD generally. There is a little bit of debate on whether it is like better for most problems, but you'll see that it actually performs a lot better on this specific task. All right, so compile again. Oh, and we have a problem.
It's the spelling of categorical.
Good call. Ooh, nice. Yes, that worked. And now we have to fit this model. So model dot. Actually, it's the same thing. Yeah, I'm just gonna go copy the other one. It looks identical. So save time. Just copy code. And let's see what this does. Cool, it looks like it's training. And you'll notice that it trains a lot slower. And that's because we added like twice as many layers. And those layers have like 10 times as many neurons. So, but you'll see, I think once the first one is done, that the accuracy is much higher at the beginning. So validation accuracy already beat the first layer, the first network. And we've only gone through one pass of the data set. So I'm going to leave that running. I'll show you it in a second. But you'll see that the accuracy actually is significantly better. Yeah, I'll come back to this in a second. So the next thing we're going to go into is the actual convolutional neural network. Kind of just basically implementing it. And you can imagine it's actually fairly similar in implementation as the fully connected networks that I was showing you, with the exception that we trade out the we add a few more types of layers. So let's see how this is doing. Now we'll come back to that. So same kind of, just define like parameters at the beginning. A batch size is 128. I don't think it really matters. As long as it can fit on in the memory of your computer, it should work. You can play around with this if you have some memory errors, by the way. So, but don't worry about that too much. Here we'll load the data. I'll wait for the stuff to finish up above. And the next thing we'll want to do is we'll want to start defining the CNN model. So let me just make sure I got this correct. All right, same thing as before. Oh, whoops, forgot a line. Define your model as a sequential model. And now we're going to add the new layer type, the conv2d. So the first parameter is going to be the number of filters. So that'll be 32, basically the number of convolutions we choose to apply to the image. The next parameter will be the filter size. So in our case, we'll just start out with a filter size of 5 by 5. So that original weight thing, just 5 by 5. We'll set our activation to equal relu again, and make sure our input shape is actually. So a key thing that I didn't talk about in the new data loader that we have is that we're not actually reshaping the data into a 784 by 784 a 784 vector. Instead, we're actually going to keep it as an image, and so we keep it in this 2D structure. And so now our input shape is 28 by 28 by 1. So the reason it's 28 by 28 by 1 is because Keras is still a little finicky and it's looking for like a 3-dimensional representation of the image, but we can just substitute that with a 1 in our case because we're only dealing with like 2D matrices since it's a black and white handwritten digit. Cool. So let's add the next layer, and since we've added a convolution and a relu, we'll now add a max pool layer. So max pool, and the way we do that is by adding a max pool 2D. And then all we need to do is pass in a filter size. So I think by default, it'll spread out the strides. Well, why don't we just define it explicitly? We'll do strides equals 2. So that means that none of the filter windows of the max pool overlap. They're just like basically one right next to each other, one after another. Then we'll add a conv2d. So, and this time we'll kind of use a trick from what people have been doing for neural networks and increase the number of filters we use in the previous layers, from the previous layers. So the idea is that you have a few more degrees of freedom to try to represent the previous input, and other than that, I don't really have an intuition on why we do that. There's a lot in deep learning to know about, like why we make certain architectural decisions. And honestly, a lot of even the field experts don't really know what's going on. So it's a new field.
Yeah, generally speaking, in convolutional neural networks, you're trying to shrink the size of your image while increasing the depth. So as you go like more and more later, and more later layers, like the depth increases, but the size of the image shrinks. So yeah.
There you go. Yeah, that was a good explanation. So after we add that convolutional layer, we're gonna add another max pool 2D, same exact deal. Make sure our strides are equal to 2. And then here's where we'll actually go back into familiar territory. We'll run this flatten layer, which basically converts the three-dimensional representation of our data that's been passed through our network here into like a nice vector that we can then apply dense layers, or the fully connected layers, as we reference them inside of this presentation. And then finally, so we first added a dense layer with 1024 units. We don't have to define an input shape because it's already implicit based on the based on how Keras structures everything. And then we add our final layer with num classes and an activation equals softmax. So first thing is I'm going to run this and make sure it worked. Cool, it seems like it's good. And the next thing is I'll go back here, and we can see the results of our classification from the previous section, and we got an accuracy of 98%. So we've already outperformed what Provin was able to do, and we were able to do it a lot faster. So don't roll your own neural network stuff. Just use Keras or use TensorFlow or use PyTorch. They're really much better than, they're really super optimized and will perform a lot better than what you can write quickly, and they allow you to write really quickly. So that's awesome. Something that I missed out on because we were still waiting for the other stuff to train was I need to run these cells, and here's the data loading, but this time we don't actually have that reshaping stuff, as I mentioned before. Cool, so this model should be set, and now we can evaluate. Maybe not. Oh, sorry. Totally missed like a key factor. There's two things I missed. I missed compiling, and I also missed the fitting part. So type this again, entropy optimizer equals atom, metrics equals accuracy. No, did I misspell it? Oh, whoops, misspelled something else. I forgot to put the metrics inside of a list. Cool, so that worked. And now I need a fit, and I luckily have it in my paste bin, so that saves me some time. And let me just make sure that this is actually the same. Yeah, it looks the same. Cool. And now it should run. And now this is going to be a little bit slower too. So this is ideally where you start using like a GPU or something like that for some accelerated speed up. So luckily you can go to, I'll just write it down here, collab.research.google.com. And then if you go to like change runtime type and go to like, oh wait, what is it? Like, it's like runtime, change runtime type. You can do hardware, acceleration, GPU. So if you want to write that down, this is the way to basically get GPU acceleration for whatever you want. And you can just upload this notebook there. The reason we didn't want to demonstrate it here is because the Wi-Fi has been really bad recently, and we didn't want to rely on Wi-Fi for this presentation. So I actually think I made a like project Python notebook that you can all check out at the very end of this, and it basically, I think it actually links to a website that tells you how to set up Google Colab with the GPU acceleration. And the great thing is, this is like, we've never seen this before. Everybody in MLab's pretty hyped about it because it's the first time you can access GPUs for free without like any complicated setup. Cool. So there's a lot of slides I have left over, and I have like 10 minutes, maybe, probably less. So I can talk about like more like CNN architectural stuff, or I can focus more on like the history of deep learning. Can we take like a vote, and maybe we can see what maybe the majority of the class would like to do? So if you would like to go into a little bit more of like architectural complexity, raise your hand now. Okay, so let's just do that. Cool. Oh, so while the CNN is training, I'll talk about this, and then afterwards we can kind of check out the progress of the CNN. Cool. So although we talked about like linear layer order, there are actually some variants of that. One such variation is called the inception layer. Basically, you take one layer and then you pass it through a bunch of different possible layers, all simultaneously, and then you can bring all of those results back together, concatenate them, basically just like throw all the matrices together, and you get your output layer. So that's really cool, and it gives you like extra expressibility, and that proved to be better on classic benchmarks. And then ResNet, another type of architecture, chooses to do kind of like a similar operation, but instead of doing like a one-by-one convolution or like a different type of convolution operation on one of the pathways, they instead just choose to copy over the input to whatever layer we had there. So that's just one kind of variation. You can find the papers here. Again, both of these seem to improve the quality of the predictions in the training process, so they seem to be good ideas. Additionally, pooling has come into question as like a necessary architectural feature. This particular paper proposes to remove all pooling and instead uses increased stride of conv layers to create the kind of like downsampling effect that you get with pooling. Read this paper if you want more information on this. So now you might be like me when I first learned this stuff and be like really confused on what you should do, like what kind of layers you should use at any point, and making all these like subtle architectural decisions that I think I basically breezed through while writing out all of this Keras code. And so like a nice principle you should use is basically this from the statement by Andre Karpathy. Basically, you should never have to train a convnet from scratch or design one from scratch. So depending on your task, mileage may vary. But what you can do is you can actually use an architecture that's been trained on like ImageNet. ImageNet's like a huge image data set. And say you need to classify dogs versus cats, which is actually part of this project thingy that I've included that you can try out afterwards. If you want to do that, you can actually start out with an architecture that's been pre-trained on this data set. And then you can just use that as like a good initialization for your layers, train at a very low learning rate, and then you'll already start out at a very high accuracy. So it's super awesome. But if you don't need to do that, and maybe you need to do something with like audio or something where there's no like available pre-trained network, in that case, you can just kind of borrow something like the inception architecture, which proved to be very good for images, and then you can try to just like co-adapt the like basic idea into whatever input data you have. So this is definitely a really good idea if you're trying to use this for research or applications or anything like that. So how to deep learn at home, basically how to do all of this stuff at home. You can run it on a CPU, and if you've been trying to do this now, you'll notice that for the convolutional neural network, which is like state of the art, it ends up being really slow. And my fan is just going wild right now with all the computation it's doing. So it's a big load, and it's not super quick. Now, your second option is to buy a GPU. This is expensive, especially because crypto miners are buying all of them up. So I think recently the price of like the baseline NVIDIA GPUs doubled in price. So that kind of sucks. And so now it's even more expensive to do this kind of stuff. Your third option is to use AWS. And before like a week ago, I would have pushed this without a doubt. And I have a nice guide on how to actually use AWS. You can check it out in the slides, which we will post after this workshop. And then now, which I don't know how long this is going to last, but Google Colab has come out, and it's super exciting. You don't have to do much to set up running a GPU. The only thing you have to do is figure out how to get your data onto that Colab instance, which is usually is a lot easier than actually setting up an AWS instance with your data on it. So that's nice. I'm gonna leave this in the slides. You can read it up. But I think it's good to kind of understand where we came from for this field. Let's see what else there is. I'm gonna have to leave this out as well. It's kind of complex. But maybe I'll end this presentation with this video. So basically, although deep learning has like a lot of good results, it's still, a lot of stuff is still unknown, and a lot of it could be really improved. And so this talk that came out from a recent conference known as, or the conference is called Neural Information Processing and Systems. This talk talks about like where we are as deep learning and kind of emphasizes that we're kind of at an early stage. We don't really know what's going on for a lot of the things that we use, and it's kind of like alchemy. Oh, whoops.
There's self-congratulatory feeling at the end. You say things like, machine learning is the new electricity. I'd like to offer another analogy. Machine learning has become alchemy. Now, alchemy is okay. Alchemy is not bad. There's a place for alchemy. Alchemy works. Alchemists invented metallurgy, ways to dye textiles, our modern glassmaking processes, and medications. Then again, alchemists also believe they can cure diseases with leeches and transmute base metals in people.
Okay. So I definitely invite you to watch the rest of that talk if you're interested. It's really cool. And kind of puts everything in perspective. So we've listed a few deep learning resources here. We actually have to add 2 more to it, so we'll make sure to do that before we send out the slides. Of course, we want to plug the rest of our workshops as well. So if you noticed in our flyer that we mentioned there's a bunch of deep learning workshop series, intro to deep learning workshop stuff. That's this exact same workshop. You don't need to come again if you are satisfied with what you've learned. But the next few that are coming up are the intro to TensorFlow, that I think that is a week from now, January 31st. We'll have intro of PyTorch, which is 2 weeks from now. Both of those are deep learning libraries similar to Keras. They're good to know, but what I think is really exciting about our workshop series are the other workshops that we have planned. So the nearest one, or the soonest one, is actually the reinforcement learning workshop that will be held in the WAS on the 15th. That's kind of like the stuff that Pravin was talking about with the Atari agent and could be the basis for self-driving cars in the future. The ones that I will be teaching will be artistic style transfer and generative adversarial networks. Those, actually, GANs, the generative adversarial network workshop, will be rescheduled, so sorry about that. But artistic style transfer will be the 22nd of February. And that's that's also a slide that Pravin brought up. And then we have all the other ones. So there's a lot of, they're all really interesting. And I think they're all very applicable for a variety of different applications. So I've added a project, as I mentioned. You can train your own deep net for cat-dog classification. You can also learn how to use GPU, AWS for GPU access, but again, Google Colab is super cool. And then I'm trying to demonstrate the performance gains of transfer learning versus training from scratch. So you can play around with that once you get access to a GPU. Cool. And I want to thank everybody for coming to this first workshop. Please check out the other workshops.